three more classes.
Including the exam, I think.
No, that can't be right. We got Tuesday, Thursday of next week.
Not including this one.
Not including this one. Tuesday, Thursday of next week. The following Thursday, because you don't have class on that one, and then the exam, right?
Yeah.
On Tuesday. We got 3 more class periods. We can do it.
So how do we accomplish?
We're on pace. We don't get it done. We're good. So the end is near. That's exciting for me. Why are you giving me that look?
I could cry.
Why? Because you're not going to have me in class anymore, so why are you going to cry?
I mean, that too, but it's mostly fear.
Fear, sadness, it's all a mixed emotion. Okay, so let's go back briefly to help us understand oogenesis. And what is oogenesis? What was spermatogenesis?
Making sperm.
Production of sperm.
It was production of spermatozoa, right? What is oogenesis?
Production of an egg.
Production of an ovum. The one thing to keep in mind, and one of the overriding kind of themes of this, as we compare this to spermatogenesis, is our ratios. So go back. What was our ratio of, say, spermatogonia A1 to spermatid?
1 to 256.
1 to 256, right? So we obviously had a huge exponential increase in numbers. The ratio was huge. Here's the biggest difference, and this is what to keep in mind. Now, we're going to have to address this as we go through how do we deal with some of this stuff. But what is the ratio of oogonia, which is where we're starting, to a mature ovum?
To 1 to 1.
1 to 1. But yet we still have the same types of steps we saw in spermatogenesis. So we keep in mind as we work through oogenesis, the ratio always stays 1 to 1. But we have to address these divisions that take place with chromosomes and splitting and all that stuff we talked about with spermatogenesis. We have to address that while maintaining the 1 to 1 ratio. And that becomes a bit of a challenge, but we will address that. Now, I like this diagram in part, but I have another one that shows, I guess, a part of this that I don't like. Up till, and this diagram is fine, but it can get a little confusing if you're not careful. Up till this point right here, or about right there, I like it. But after that point, it can get confusing because they, for whatever reason, and this is physiologically correct, but from understanding the process, this can confuse you, is they add this concept of fertilization into it. So we're introducing more chromosomes. That can get confusing. So we'll work through that, kind of work around that so you understand what would happen if we did not have fertilization. But let's start here. Now, one thing to keep in mind is this dotted line. This dotted line is important because this dotted line, depending on the animal, whether it's humans, in humans it would be years, in certain animals it would be months, but that dotted line represents a long period of time that there's no point in even having that on this diagram because nothing is happening. So if you look over here on the left side, this time period is fetal phase. This starts puberty. So if that arrow right there ends basically at birth, which it is, when fetal period's over, that's birth. So that end of that first arrow right there is birth, but the top of that arrow below it is the beginning of puberty. So what is represented by that dotted line? The period of time between what and what?
Birth and puberty.
Birth and puberty. But between birth and puberty, nothing happens. So why put it on this diagram? Does that make sense? That's why that dotted line is there, representing that at birth, and this is true of not just mammalians, although that's our focus today with this, but also in birds. At birth and or hatch, all the potential ova that will ever be produced in that animal's life are already there. No more is going to develop after birth. So there's a period of between birth and puberty that, because of what we talked about earlier about puberty, there's no hormone levels to generate any continuation of oogenesis, so nothing's really happening. But this is representing the fact that at birth, all the potential ova that would ever be produced are already there in the female, in the form of what we call primary oocytes. So we all start with an oogonium. That is the germ cell, very similar to what we see in the spermatogenesis. Note it is diploid. This undergoes, during fetal phase, it undergoes just simple mitotic divisions. It's just replicating itself. Replicate, replicate, replicate. It depends on the species. It depends on the individual. Then the species, how many primary oocytes you're actually going to get at birth. But obviously there's a lot more that are going to be potentially there in an ovary that that animal would ever ovulate in her lifetime. But this fetal phase is all just a mitotic division where we're just replicating them, going from 2 end to 2 end, 2 end to 2 end, nothing fancy. But we end at this primary oocyte stage. We then have that period from birth to puberty where nothing's happening. We have a bunch of primary oocytes just sitting there waiting. What are they waiting on? What are the primary oocytes waiting on?
Hormone.
What hormone are they waiting on?
FSH.
They're waiting on FSH. Yeah, that's what they're waiting on. And obviously, as we get into puberty, we're going to have, we already talked about this, we're going to have increasing levels of FSH. It's going to stimulate the process to start again. And this is the beginning at this point at the beginning of puberty. Okay? So primary oocyte begins to change. But the first thing that primary oocyte, and this is going to be important for us next time particularly, the primary oocyte is going to gain something. And the thing it gains is very important for it relative to fertilization. And it is called the zona pellucida, that dark, that black, thick shell. And it is somewhat of a shell. It's not calcium, it's protein. But it's a proteinaceous shell that forms around an oocyte. Why is that important? Well, it's kind of a hard proteinaceous shell. What would that do for, what does a shell do for an egg? It protects it. But it needs to protect it all the way through fertilization and even into early embryogenesis. So here's the challenge for the sperm. This thing is covered by this hard proteinaceous shell. What does the sperm have to do? They somehow have to get through it. So that's going to be the first thing they have to address as fertilization begins. So what comes into play at that point? Not to jump too far ahead, but
Enzymes.
enzymes, and where will those enzymes be located?
Acrosome.
In the acrosome, okay. So we'll talk more about that next time when we talk about fertilization. But zona pellucida is the first thing it develops, and then there's this proteinaceous shell that is there to protect this oocyte. Now we will look at some other cells on the next couple slides, or on the third slide, relative to some supporting cells that relate to protection as well. So here's starting the division steps. We go into meiosis 1. Now let's back up. What did we say meiosis 1 was? What was meiosis 1? Okay, it is diploid to haploid. Diploid to haploid. So 2N to 1N. So we're taking half the chromosomes, half of them are putting over here, half of them are putting over here to make 2 1Ns. The 2N goes to a 1N and a 1N. Okay? That's meiosis 1. Here's the problem. What ratio do we have to maintain?
1 to 1.
1 to 1. In spermatogenesis, we was easy. We just had one thing that was 2N, and we made 2 things that were 1N. That was easy. But it wasn't 1 to 1 ratio. So how do we address this? If we've got eraser, why are they all the way down here? And I've got a wall all the way down there. Something we need to complain about. Okay, so if we've got 2N, and I'm going 1N and 1N, I got to maintain a 1 to 1 ratio though. So what do I do with some of this chromosome? Do what? Did you say? Well, no. I think I heard what you said, and I think it's funny you said that because that's kind of what happens. She said, "Did you say throw it away?" Yeah. That's kind of what she's got to do. She's got to throw it because we don't need it anymore. But it still has to divide. So what does the oocyte do with this? She forms what's called a polar body. See that little black spot right there? That's a polar body. What is that polar body? It is chromosomes with no cytoplasm in it. Just chromosomes packed together in a little package. Why is it packed together in a little package? Because it is a way we're going to trash it. She will eventually dump all that. but we can still maintain that 1-to-1 ratio. So that 2N right there, half of it went where? To the nucleus of that secondary oocyte, right? Where did the other N go?
First polar body.
Into that polar body. Does that make sense? Now that polar body will eventually disappear. She literally will produce some enzymes, we'll talk some about today and next time as well, that will degrade that polar body. It is a place to shove it to get rid of it. But she's got to maintain the 1-to-1 ratio. Now do not, you're welcome to learn this, I don't care, I'm not going to hold you responsible for this. Don't let this confuse you either. This just shows you with the main 4 species we would deal with where ovulation would take place in this particular process. I'm not that worried about that. So don't let that confuse you all this stuff over here. Focus on what's going on in the middle. So after meiosis 1, we have a primary oocyte going to a secondary oocyte plus the first polar body. Now here's where it becomes confusing, because now they're jumping into meiosis 2, but they're adding fertilization into it also. They're adding chromosomes from that. So that's where it gets confusing. So let's focus not on this bottom. Let's just kind of draw it a little bit. So if I go, so I've got, I won't draw it very well, but there's my secondary oocyte, and they'll make a little polar body right there. Okay? That's at the end of meiosis 1. Now, what did we say meiosis 2 was? What did we say meiosis 2 was?
Haploid to haploid.
It's just a mitotic division. It's just replicating everything. How do I replicate this structure and keep the 1-to-1 ratio?
Another polar body.
We have another polar body. If we replicate that N right there, we then have an N with the original polar body, right? Plus another polar body because we replicated this, but we don't want 2 of these things, so we got to shove more of that down here. And here's where it gets even more confusing. This is chromosomes. This is subject to mitosis as well. So this can actually replicate itself. So what does that result in? 3 polar bodies. Some of you look confused.
Will it always do that, or is that just sometimes?
Good question. She said, "What? Are you talking about the polar bodies?"
Yes.
Yeah.
third polar
That
body.
one's a tough question to answer. It depends on the species. Some species it does, some it does not. That's what gets confusing. And sometimes this polar body will start to degrade before meiosis 2, and so because it's degraded so much, it won't replicate.
So
Does that make
only
sense?
the original one will replicate itself?
The original what?
Polar body?
Yeah, as far as polar body replication, yeah, if it hasn't started to degrade yet, it will replicate itself in meiosis 2, in meiosis 2, which is mitotic. Okay, so let me go through that one more time. Some of you look. Everybody good right there? That's a secondary oocyte with a polar body. Are you good with how we got there? Okay. So meiosis 2 is mitotic division. So everything's just replicated. Just like you're just making a mirror image of this. Remember, 1-to-1 ratio. So we can't make 2 of these. We've got to continue 1-to-1 ratio. So what do we get? If we double this, replicate it, making 2 of them, well, we can't have 2 structures, so what do? Half of that, or one of them if you will, goes in the middle and makes the nucleus. The other one, make that polar body there, the other one's going to form another polar body. Now again, this polar body may or may not replicate. If it does replicate, we actually get 3 polar bodies. If it doesn't replicate, because it's already degraded, we don't get 3 polar bodies. So it's, yeah, I know you're like, that's confusing, but I know it. That's biology, I guess. Sometimes you'll have 3 polar bodies, sometimes you won't have 3 polar bodies.
Will the third oocyte also be used?
The third.
Because if your polar body goes through mitotic division as well, you'll have another polar body and then another oocyte. So you'll have 3 oocytes and 3 polar bodies, right?
You lost me on that one.
It doesn't keep going after that, it stops.
No, it doesn't keep going after that.
Well, no, I don't know. Never mind. Well,
I
okay.
totally, you lost me on that one.
So you have one polar body
Here,
because it originally had a polar body, right?
No. No, back up here. This polar body right here resulted from this meiotic
Right, it's the
division.
second one.
Yeah.
So, you're supposed to have at least 3 in the bottom?
No, that again, that's where it gets
Sometimes
confusing.
3,
You're
always
gonna
at least 2.
have 2. You may have 3.
Right, but it was basically where you took 1 and made 2, and then 2 technically makes 4, but if 1.
Yeah, you're right.
Okay.
No, I see what you're saying. Yeah.
Okay.
You're thinking about that right.
Okay.
But remember, this one doesn't always replicate. Depends on how much it's been degraded. So there's a gray. There's always gray in that. It is what it is. See, for instance, that shows 2 polar bodies down there. Well, that just happens to be an example of that first polar body started to degrade, so it never replicated. But show you on this next slide, just to show you, this is out of a biology textbook. Notice here, it's showing 3 polar bodies. That's more typical. There's one polar body that's replicating itself there, and that's the other one. So it varies a little bit. So it's not, that's kind of thing's not set in stone. Now let me go back to this, to avoid any confusion. What is the deal here? Having established that, okay, so we're here, given that extra polar body or not, okay? If you want to go with extra polar body, that's fine. If not, again, it's great. But let's say this right here should be right here, right? Except for what happened.
The sperm fertilized you.
Right, so notice this is N with 3 polar bodies, or it could be 2 polar bodies again. This is 2N. Why is this 2N? Because we had fertilization. Does that make sense? So understand that. That's where that 2N at the bottom comes from, only because of fertilization. You could actually shove this right here in, right above that, right up here, introduce the sperm, then you make the 2N or restore the 2N state. Does that make sense? Does this whole thing make sense? Again, it's the same basic stuff going on in spermatogenesis. You're just maintaining a 1-to-1 ratio, but formation of those polar bodies is the key to keeping that 1-to-1 ratio, because when we replicate things, whether it be in meiosis 1 or meiosis 2, we've got to deal with all this extra chromosomes. So we form these little packages that have no cytoplasm in it. It's just a package, it's like a garbage can. A package we're shoving in a specialized space of the oocyte, and we're going to eventually throw that away. She's going to eventually degrade that because we don't need it anymore. So that is oogenesis. So part of it is simpler than spermatogenesis. There's no numbers to remember. It's 1-to-1. But certainly, the polar bodies cause a bit of a challenge to understand that. Questions at all on that?
Okay.
So,
Sorry. So all the polar bodies are the exact same, right?
Yes.
Okay. So how would you refer to them? Like, what would their names be if you're trying to talk about a specific one?
That's a good question. This is the first polar body, polar body 1.
Uh-huh.
The other 2, I don't know. I don't know if they 2 and 3, but I don't know how you would differentiate necessarily
Okay.
between the 2. Polar bodies tend to be, they're, for the most part, they're fairly unimportant. They're just a means to an end, I guess,
Okay.
to get rid of it. So I don't even know if I've ever, I may be wrong, I don't know if I've ever seen them designated other than just like first, second, third polar body.
Okay.
Unlike the spermatogenesis, you had all that spermatic component and all that. Any other questions at all on this?
now at the bottom where it says zygote and second polar
Right.
body, is that how that would be worded, or would it be like?
Yes, why would it be worded zygote? And I don't want to jump ahead with our terminology, but
Fertilize.
Like if it didn't have fertilization, it wouldn't be called that. Would it just be
No.
called
it would
third
be
oocyte?
No, it'd be a secondary oocyte. It'd still be a secondary oocyte. It would be a non-fertilized secondary oocyte.
Okay.
Now, I don't want to jump too far ahead. There are some intermediate terms we'll get to, because there's a structure that will form, there is a phase that will form between that secondary oocyte and fertilization. Between that secondary oocyte and after fertilization before the zygote stage, where the nucleus of the sperm and the nucleus of the oocyte are not fused yet. That was called oocyte. But we'll get to that when we talk about early embryogenesis. Anything else on that?
So it wouldn't be fertilized until after it had at least 2. Okay.
Well, no. I checked my head too fast. It depends on the species. In some species it is, in some species it doesn't.
The 2 or the 3?
Usually you'll always have at least one polar body before fertilization starts.
Okay, so you can fertilize before meiosis 2 happens?
Depends on the animal a little bit. Depends on the
Okay.
species. I'll show you. I'm trying to avoid getting too far in the weeds for next time. You'll see next time we actually have meiosis II taking place in the middle of fertilization.
Okay.
So it's hard to define beginning versus end.
Exactly when.
It's
yeah.
in the middle,
Okay.
more or less. You'll see that next time you can track it because they leave the whole body.
So, in order for fertilization to happen, you have to at least reach the top one, right? Or no?
Yes,
Okay.
like you hit this.
Meiosis
Yeah,
one.
yeah.
Okay.
Because you've got to get it into a haploid state.
Okay.
Yeah, absolutely. Anything else on this? I want everybody to understand. Any questions? Okay. Don't worry about this next one. I mean, you're certainly welcome. There's nothing wrong with this slide. The only reason why I threw that in there is to show you the formation potential of three polar bodies. So don't freak out about this. I really want you to focus on the other one because it gets to show a little more detail. Okay, the last thing, well, there's one more slide I want to briefly mention after this, but I want to focus on this, and this is going to be a jumping off point for us next time because a lot of this ovum anatomy stuff actually relates to fertilization. In fact, some of this stuff is directly related to fertilization. Let's start on the outside. This is an ovum. Obviously, the ovulation has already taken place. We alluded to some of this earlier on with the supporting network of cells that surround the ovum. An oocyte is quite large. It's a big, huge cell. So you'll notice how big it is compared with these smaller, quote-unquote, normal cells. But I want you to focus on these supporting cells, and that's all they are. There's a cumulus mass, which are these loosely connected cells all around it. And there's this tighter single layer of cells, if I can hold that steady, right there. They're more organized. Single layer all the way around called the corona radiata. Okay, corona like around the sun. The corona radiata and the cumulus mass are supporting cells. And what is their job? If you think about when this ovum was attached to the base of that follicle, they were attached to the base of that follicle by way of some of these cells. If you remember early on when we talked about ovulation, we talked about breaking gap junctions, and we'll talk about that later. Well, that's kind of what we're going to talk about now and next time. Is what happens, these cumulus cells are connected to the base of the follicle by way of gap junctions. When ovulation takes place, those gap junctions break. That allows the ovum to actually be free at that point. But these cells stick with the ovum for a while. I say for a while. What's the purpose of these supporting cells? What do you think the most obvious purpose of these supporting cells are?
Are they the shell for protection?
Well, they're not a shell because the zona is already on there. See that line right there? That's the zona pellucida. It's already on there. These are on top of the zona pellucida. But you're right. Their job is to protect as well. And more correctly, these cumulus cells actually act as a shock absorber because this ovum is going to go through a lot of physical stress as it's moving through the oviduct. And so a lot of those cumulus cells will get knocked off, but when they're doing that, they're absorbing that kinetic energy to act as shock absorbers. This corona radiata, those will stay with it till the very end, or at least until fertilization. So what kind of a challenge does this cause sperm cells? If that cumulus mass is still some of it there at fertilization, which a little of it is, we know the corona radiata is going to be there at fertilization. What challenge does that cause sperm cells, or does it cause them a challenge?
Yes.
Yeah, there are cells that sperm cells have to get through. How are they going to do that?
With the enzymes?
They're going to use enzymes. We'll talk about the specific one next time. They're going to use enzymes that literally kind of melt those cells away so they can get through there. Then they get to that zona pellucida, and then they use other enzymes to get through it, and then we'll talk about all that next time. But all these supporting cells, the cumulus mass, which is a loose cumulus sprinted cloud-like, a loose network of cells, as well as the corona radiata, they are support cells. They're there principally to protect the ovum. Specifically, though, the cumulus mass, that is actually going to act more as a shock absorber as this ovum kind of bounces along the oviduct. After that is the ovum, at least the components more critical for us, the cumulus, or the zona pellucida here, which is that proteinaceous shell that sperm cells obviously have to get through. Then you have a space after that zona pellucida. That's that area right here. That's an open space called the perivitelum space. Peri referring to around the vitellum membrane. The perivitelline space. That is the location of the polar bodies. It's not a very hospitable environment for anything. It's not hospitable for a polar body. It's not hospitable for sperm cells. If a sperm cell gets caught in that perivitelline space, and this will happen, what's going to happen to that sperm cell?
Degrades.
It's dead. Why is it going to die?
It gets degraded.
It's going to die for the same reason the polar body is going to die, because she's going to produce enzymes. She, meaning that ovum, is going to produce enzymes. We'll talk about this process next time. It's going to kill pretty much anything in it. Kill sperm cells, degrade them. Kill polar bodies, degrade them. Okay. So the perivitelline space is a fairly harsh environment. Now, when we get to fertilization, we'll talk about these different mechanisms to prevent polyspermy. What is polyspermy? And why is polyspermy bad? Or is polyspermy bad?
Many sperm on one egg.
Yeah, polyspermy is when more than one sperm cell gets into the cytoplasm. Do we want that to happen?
No,
Why do we not want polyspermy?
because only one can fertilize.
Well, she said only because one can fertilize. She's kind of correct, but if we have polyspermy, that means more than one sperm cell gets in the cytoplasm.
Yeah.
So now we have 2 nuclei from sperm cells plus the nucleus from the ovum. Is that a problem?
Yes, because they have multiple chromosomes.
Yeah, then you got a 3 end state. And that's too many chromosomes. So that leads to abnormalities, or it leads to zygote death typically, because it's not normal. So should we have mechanisms to prevent that?
Yes.
Yeah, and we do. And we'll talk about that next time. But there's a couple of blocking mechanisms. One is the primary, one is a backup system to prevent polyspermy. We want one sperm cell to get into that cytoplasm. Anything beyond that is abnormal. There will be sperm cells that get trapped in that perivitelline space. There will be sperm cells they're sad. These are the sad guys. I feel bad for them. If you get trapped in the perivitelline space, that really sucks for you. But I think maybe even worse than that is the ones before that get trapped in the zona pellucida and they can't dig through anymore because it's been shut off from them. Because one beat them to it. And they're just stuck there. They're literally stuck to an oocyte and can't do anything. I don't know which is worse. Being killed or just stuck. I don't know. But there are mechanisms to prevent polyspermy, and we'll talk more about that. So the perivitelline space is going to be important to that effect. Now the ovum proper starts at that vitellin membrane, which is that thin line right there. That's the ovum proper. And then you've got these cortical granules. Now again, we'll talk about those next time as well. Those cortical granules are little enzyme-filled packets. They have strong enzymes, and they're like soldiers almost. They're lined up protecting, and that's really what they do. They're enzymatic protection, because what will happen during some of these blockage processes, the enzymes that are in those cortical granules will be released out into the perivitelline space, so they go that direction, out into this space, and it will destroy anything in the perivitelline space. So they're little bags of really strong enzymes. And then, of course, you have the cytoplasm here, and you've got the nucleus there. So ultimately, we want one sperm cell to get into the cytoplasm. That's the one sperm cell that will fertilize or undergo fusion with the nucleus of the ovum to form a zygote. So this lays out for you some basic ovum anatomy. Now keep this in mind next time, because we're going to come back and revisit a lot of this, because that's involved with fertilization. One last thing we'll mention is, and we kind of touched on some of this, at least indirectly, is transportation of an oocyte particularly within the oviduct. The oviduct itself has specialized epithelial cells. It has cilia on them. What are cilia?
Those are the spirals that keep the ovum intact, right?
With finger-like projection.
It's like a little finger. You know that from biology, right? We have them like in your lungs and all that stuff. Yeah. The lining of the infundibulum, of the oviduct is highly ciliated. Why is that important?
So, catch the sperm cell?
Not as much the sperm cell.
Because it keeps the ovum.
Yeah, it helps move. It's like move. They're like little fingers that kind of throw it lightly. Yeah, it helps move. I always think of this as like, if you go to Kansas and when the wheat is out and you see the wind blowing, that reminds me of cilia. And if I were to throw a big beach ball, in that we'll call it, can you just visualize this, right?
Mhm.
The beach ball being blown through that field of wheat. Are y'all with me?
Yeah.
I always like to hear it say. That's kind of the same thing. But what do we add to this mix? We have oviductal fluid as well. So the cilia is kind of bathed in this fluid. All that helps to transport this ovum or zygote, because fertilization is going to take place obviously in the oviduct, so depending on when it happens. But there are mechanisms there to help move an oocyte or a zygote along that infundibulum, as well as the peristaltic action, that contractile action of the oviduct as well. All that helps to move the oocyte, and then ultimately, hopefully, after fertilization, the zygote along towards the uterus. We'll come back to some of this when we talk about early embryogenesis and give you an idea of where some of this takes place in the oviduct. But I just want to mention some of that stuff as kind of a ending point. Next time we will start off talking about fertilization. We'll come back to that anatomy stuff of the ovum and jump into the steps in fertilization. Then we'll go into early embryogenesis, look at our extraembryonic membranes, and then into placentation. So we'll cover more next time. But we'll finish up this slide set we're on right now next time. So I will see you on Tuesday unless you have any more questions. If you do not, have a great weekend.